Welcome back to CH5010. We are discussing fixed bed reactors. So compared to what I said yesterday, just a slight change is we will kind of solve, not exactly a tutorial problem, but something. Today's session will be something like tutorial. Okay, as I was just saying, uh, yeah. If you look at the problem sheet for today, this is not a graded sheet. This is an example. We are looking at uh, fixed bed reactor. Okay, so we are going to look at a reactor, and first case we are going to consider if there was no mass transfer limitation. This is nothing but PFR. Okay, this is something that we have done in module 8. Okay, so the inlet flow rate is given, I think 12. FA in CA in is given. Your reaction rate is R K times CA. Okay, so that is given, and you have to find the size of the reactor to get 80% conversion. Okay, so that is the first problem. Second problem is, let us say that the fixed bed reactor consisted of had of size something, that size is given to you. Okay, so let's look at the pellet. Okay, what we have done in module 5b to look at Thiele modulus or generalized Thiele modulus. Okay, you can just use generalized Thiele modulus over here. Let's not worry about Thiele generalized Thiele modulus and eta. Okay, now let us say that this FBR, this is pellet. Okay, now let us say that this fixed bed reactor contained these pellets. First problem we have just talked about, it's treat it like a PFR, don't worry about what is contained in the PFR. Now we are saying actually in the PFR you have pellets and there is diffusion and reaction that is taking place in the pellet. Because of internal diffusion limitation, from problem 2 we realized that effectiveness factor, let us say, is 0.8. If the effectiveness factor is 0.8, then the rate of reaction is reduced by a factor of 80% or by a factor of 20%. It is reduced to 80% of the original. Okay. So, what is the new reaction rate? It is, instead of K multiplied by Ca, it is eta multiplied by K multiplied by Ca. Okay. A large part of homogeneous models essentially are going to replace R with eta multiplied by R. That is how you do homogeneous models. Okay. What are homogeneous models, heterogeneous models, how to approach all of that, we will come to in the next lecture. Okay. What if you do not want to use or cannot because of the physics? Okay. In that case, can look at this as a reactor, and let's say there are pellets. Okay. This pellet, let's say it's a spherical pellet. You just expand this, okay, and you have diffusion to the pellet, that's external diffusion, and diffusion inside the pellet, that is internal diffusion. Okay. So, if the concentration over here, gas phase concentration over here is Ca, the surface phase concentration is Cas, and within the pellet the concentration okay, depending on what level of models you take. If you take, if Ca in bulk is said to be approximately equal to Cas, then you get homogeneous model. You will get 1D heterogeneous models. If you have to include simulations of internal diffusion also, then you get one D plus 1D hetero models. Okay. I'll come to this slide. I know some of you are writing. Okay. This is what the comparison between homogeneous and heterogeneous is. Okay. This is what the pseudo homogeneous model or homogenized models are going to be, exactly what I've been just talking about over the last few minutes. Okay. This is how you're going to model the systems. This was an example I think I took last year based on, again, this was based on student request. So we took this particular example, and yeah, and accounting for mass transfer, accounting for pressure drop, and then we started talking about axial dispersion models also. Okay. All of this is there. You can pre-read it. Some of it is going to be a little bit confusing. So we will go over that on Monday. Okay. Monday we will go over it. If you do get time, maybe Davis and Davis. I think the treatment in Davis and Davis. Yeah. I think the overall treatment is in Davis and Davis is a little bit too basic, and therefore it is much more readable. The treatment in Froment and Bischoff is much more applicable to industry and in research. Much more in industry. Froment in Belgium and Bischoff in US. They work quite closely with industries in Belgium and Netherlands in case of Froment, and companies like DuPont in case of Bischoff. They work quite closely with the companies, and therefore lot of their work is actually quite motivated by real problems in petrochemical and polymer industries. Okay. So a lot of the treatment in Froment and Bischoff in these chapters come from that angle. You will see that lot more space in Froment and Bischoff is dedicated to heterogeneous and reactions and heterogeneous catalysis than the homogeneous catalysis, and that's kind of the reason behind this. So it has a little bit advanced treatment, and therefore it's a little bit difficult to read. But if you get time, do glance. I'm not asking you to spend more than half an hour, okay, on Davis and Davis. I mean that's all I'm asking you to spend. Just spend about half an hour on chapter 10 of Davis and Davis, okay, if you have time. I know we're coming close to end of the semester, so time is very premium. So find some half an hour very quickly today, let's say, okay, so that you can enjoy Diwali tomorrow and on Friday. Half an hour, 20 minutes, 25 minutes, just 3-4 of you sit together, look at Davis and Davis's book. That will have a lot of useful things for you. So that's my suggestion for you. I'll just move this a little bit so that it will be easier for you to read after this. Okay. So just to go over fixed bed modeling, we've talked about the fixed bed. We talked of the various processes in the fixed bed. Then we are going to talk about the example. I'll use black font here. This is the example sheet that says 30th October. Okay. Problem number 1, exactly what you did in module 1 and module 8, simple PFR. Okay. The fact that it is a fixed bed reactor or homogeneous reactor, it just doesn't matter. Your K is given to you, Fin is given to you. You want to calculate the volume of the PFR for achieving 80% conversion. That's the straightforward problem. That is that problem 1. Problem 2 is a straightforward problem from module 5B, that if this particular reactor was a fixed bed reactor with catalyst pellets of 3 mm diameter, then will there be mass transfer limitation? If there is mass transfer limitation, what is the effectiveness factor? Again, I don't know what the effectiveness factor is, but let's say the effectiveness factor is 0.8. That means that the rate constant is not 2.4, but the rate constant, the realistic rate constant that all of your reactants will see is eta multiplied by K. Okay, so your rate of reaction is reduced by 20% because your effectiveness factor is 0.8. So there is a net rate reduction in rate of reaction. If there is net reduction in rate of reaction, how do you calculate the PFR? The PFR you will calculate exactly in the same way. Instead of K being 2.4, you will have eta K, which is 0.8 multiplied by 2.4. So that's what you are going to do today. This is not a tutorial. This is just an example session. Tutorial will come next week, where I will modify the problem slightly, keeping all the numbers very similar, but modify the problem slightly so that it has the parameters and so on are going to become a little bit more realistic. Lot of times in literature, people report rate of reaction not in terms of kCa, but in terms of K double dash, which is the rate of reaction is in moles per kg catalyst per second, not in terms of moles per meter square per second. Okay, so that's if you have a situation like this, how do you handle that is what we will take up as the tutorial problem. If you solve this particular problem, solving tutorial problem will be quick because all of the numbers will be the same. You will just have a few more calculations to get those numbers. Okay, so that's the game plan for us for now. Okay, so and get started with the problem sheet. And then this particular slide is to talk about what's coming next, and what's coming next is there in the slides. Okay, So you don't have to submit these sheets, you take these sheets with you. If you have not completed solving them, just finish off the solving of the problem. Okay. So these are the problems that I said. Okay.